Okay, now in this video I will teach you the determination of basic radicals. Okay, so you can see that I have made a huge table over here. So let me explain now. So the basic radicals are divided into 7 groups. Okay, the first group is the 0th group and the last group is the 6th group. The radicals are divided in these groups on the basis of their common reagent by which they are precipitated or identified, which is the preliminary test. Okay, for the test of all these radicals I will make another separate video along with the demonstration. This is just an introduction. So first we have group 0. In what we do, first we take some salt in a test tube and add sodium hydroxide solution into it and boil it. If on boiling, ammonia gas is evolved, which can be identified by its smell, or a litmus paper, or a glass or dipped in hydrochloric acid, then densified from the evolved. So the basic radical could be ammonium. Ammonium could be present. After you have tested for the 0th group, which is ammonium radical, then we can prepare the original solution. So for preparing original solution, we have to make the solution of that salt or that salt mixture in water. If the mixture is insoluble in water, then we try the dissolving the mixture or the salt in dilute HCl. If it's not even soluble in dilute HCl, then we try dissolving it in dilute HNO3. If it is not soluble in dilute HNO3, then we try it in concentrated nitric acid, and if it is not insoluble even in concentrated nitric acid, then we try dissolving it in aqua regia. Okay, but we avoid making original solution of the salt in nitric acid and aqua regia. Why? Because when we will pass hydrogen sulfide in second group, hydrogen sulfide can get oxidized to sulfur. That's why we prefer making original solution either in water, and if it does not dissolve in water, then in dilute HCl. Right? If it does not dissolve in cold dilute HCl, we try heating it and see if it can dissolve in boiling hot dilute HCl. Then only we proceed to the nitric acid group. Then only we proceed to making original solution in nitric acid and aqua regia. Okay. So now, after we have prepared the original solution, we start the group analysis. So first, we take the original solution and add dilute HCl into it, which is the group reagent of first group. Okay. If on adding dilute HCl, a PPT is involved. A PPT is formed, which will be white. Then you may infer that group 1 is present. The white PPT could be of lead chloride, silver chloride, or mercury 1 chloride. Okay, so these are the cations or acid, basic radicals which are precipitated in group 1 as chlorides. Okay, now then we move to the group 2. So if something is precipitated in group 1, we filter that precipitate and take the filtrate and then pass H2S into it. If not, we don't filter it and directly pass H2S in it. In presence of dilute HCl, the concentration of the sulfide ions is reduced due to common ion effect to that extent that only these radicals, sulfides of these radicals, are precipitated. Okay. So what are these radicals? These are lead, copper, mercury 2+, cadmium 2+, bismuth 3+, antimony 3+, 5+, arsenic 3+, 5+, and tin 2+, and 4+. Now you can see that lead is there in group 1 as well as group 2. Over here also lead is in divalent state, and here also lead is in divalent state. This happens because lead chloride is partially soluble in water. So lead ions are not completely precipitated in group 1, and if lead is present, it will be precipitated in group 1 as well as in group 2, because it does not get completely precipitated in group 1 as lead chloride. So it will form a black PPT of lead sulfide in group 2 also. Okay. Now you can see that Mercury is in group 1 also and Mercury is in group 2 also. But over here in group 1 Mercury is in +1 state and in group 2 Mercury is in +2 state. Okay. Now you can see that I have classified basic radicals from lead to bismuth in group 2A and antimony to tin in group 2B. Now why is this classification done? So you can see that group 2 is a very big group, right? There are a lot of cations in this group. So we have classified this group, we have done a subdivision in this group as group 2A and group 2B. So what happens when group 2 gets precipitated, we add ammonium polysulfide solution into it. So the sulfides of the group 2B gets dissolved into ammonium polysulfide solution, leaving the sulfides of group 2A behind, and we can filter that solution to separate group 2A from group 2B, right? So that's why this group is called 2A and that group is called group 2B. This group is also called the copper group. Group 2A or copper group, and that group is also called as the arsenic group. Now, after we have done the analysis of group 1 and group 2, then we have to remove the interfering radicals if they are present. If you have not seen my video on acidic radicals, I have told that first we do the analysis of acidic radicals, then only we move to the basic radicals. Why? Because we have to identify the interfering radicals if they are present or not. If they are present, then we have to remove them after group 2. Otherwise, they will create a problem in our analysis of further basic radicals. Then we have to boil off the hydrogen sulfide. If they are not, if interfering radicals not present or they are present, anyways, we have to boil off hydrogen sulfide and then add concentrated nitric acid and boil it. Concentrated nitric acid is added here to convert the iron from +2 state to +3 state. Now it can have what happens? Suppose you are given an iron 3 salt, but on adding on passing hydrogen sulfide, what happens that due to reducing nature of hydrogen sulfide, iron 3 plus will get reduced to iron 2 plus. So concentrated nitric acid is added to oxidize the iron 2 plus and back into iron 3 plus, right? After we have done this, we cool down the solution and then we proceed with the test of group 3. Now the group reagent for the group 3 is ammonium chloride plus ammonium hydroxide. Now ammonium chloride over here is added to lower the concentration of OH minus ions produced by ammonium hydroxide. By common ion effect, if you have studied what is common ion effect, then you might know. Otherwise, give me 1 minute, I just explain what is common ion effect. So I am rubbing this. So what is common ion effect? So what happens? Suppose you have a weak acid or a strong acid. For example, over here, now HCl, you know, it is a strong acid. H plus plus Cl minus ions. It dissociates into H plus and Cl minus ions. Now H2S is a weak acid. It dissociates into H plus and sulfide ions. Okay. Now HCl, when HCl is added, it increases the concentration of H plus ions. Now due to the increase in the concentration of H plus ions, this equilibrium shifts to left side. The result of this equilibrium shift is that the concentration of the sulfide ions also gets lowered to that extent that the sulfides of only group 2 are precipitated, whereas the sulfides of group 4 remain in solution. In same way, ammonium chloride and ammonium hydroxide also works. Okay, I am writing it here. NH4Cl gives ammonium ions plus Cl minus ions, and NH4OH gives NH4 ions plus OH minus ions. Now, over here the concentration of ammonium ions is given by ammonium chloride, which results in the equilibrium shift from towards the left side, and the result of which is the concentration of OH minus ion gets so low that only hydroxides of the group 3, which is aluminium, iron and chromium, in trivalent state gets precipitated, whereas the hydroxides of group 4 are not precipitated. If you will add ammonium hydroxide directly, the hydroxides of nickel, cobalt, manganese and zinc will also get precipitated. Now, after we have done the analysis of group 3, we filter the solution if any precipitate is formed. Now, in all these 3 ions, different color precipitate is formed. In case of aluminium, a white gelatinous precipitate is formed. In case of iron 3+, reddish brown precipitate of iron 3 hydroxide is formed. In case of chromium 3+ ion, gray green color precipitate is formed. So we can identify, we can have a guess of the basic radical by the color of the precipitated hydroxide. In same way, we can also have a look at the color of the sulfides and estimate which sulfide or which basic radical would be present. For example, lead, copper, mercury and bismuth sulfides are black in color, whereas cadmium sulfide is yellow in color. Antimony 3+ sulfide, antimony 3 sulfide is orange in color, and arsenic sulfide is yellow in color and brown in color. And tin sulfide, not if tin sulfide, that is tin 2 sulfide, it is also I think yellow in color or maybe brown in color. Yeah. Now we proceed to the group 4. Now we have already alkaline our solution with ammonium hydroxide. Now we pass H2S into that solution. Now on passing H2S, this time dilute HCl is not present. Instead, base is present. So due to this base, the concentration of sulfide ion gets high, and then sulfides of nickel, cobalt, manganese and zinc are precipitated. Now nickel sulfide and cobalt sulfide are black in color, whereas manganese sulfide is buff in color. Buff color is a flesh-like color, and zinc sulfide is a white color precipitate. We filter that precipitate and then we start with the analysis of group 5. Right? Now the reagent for group 5 is ammonium chloride plus ammonium hydroxide plus ammonium carbonate. Now we can either boil up the H2S and then add ammonium carbonate, and we can also add ammonium carbonate directly into it, because now H2S will not hinder in our test, right? So on adding ammonium carbonate, now again common ion effect takes place over here. We use ammonium carbonate, so what happens, the concentration of carbon ions gets suppressed, so magnesium carbonate does not get precipitated over here, and only barium, strontium and calcium carbonates are separated over here. Now we filter these precipitates and then check for barium, strontium and calcium in the same order, barium, strontium, and then we check for calcium. The detailed test I will be uploading later on along with the demonstration. Then after we have tested for group 5 and filtered that solution, Now we come to group 6. Now group 6 is a special group as we did in the acidic radical group. So over here group 6 does not have any common reagent, and these are the ions: magnesium, lithium, sodium and potassium. Okay, now there is a reagent for magnesium ion. So you can you know that already we have ammonium chloride and ammonium hydroxide into our solution. We add sodium disodium hydrogen phosphate into it, so a crystalline precipitate of magnesium ammonium phosphate is formed. So in that way we test for magnesium ions. So this reagent is only for testing magnesium ions, and lithium, sodium and potassium are tested by flame tests, and there are also some different tests which I will be demonstrating in my other video. Okay, so this was the determination of basic radicals, and it was just an introductory video. I will be making detailed video of all these basic radicals and acidic radicals in my future videos along with the demonstration.